Welcome back for another deep dive. Today we're going to be tackling something pretty dense,
Oh, yeah.
gauge theory.
Okay.
And you've been interested in understanding its importance in modern physics,
hmm
especially when it comes to the standard model of particle physics. And
hmm
trust me, it's a fascinating journey, even if it can seem a bit abstract
Mm.
at first.
Okay.
The core idea is this.
Okay.
Gauge theory is like using a redundant language where different descriptions can represent the same physical state.
Go
It's like having multiple paths that all lead you to the same destination.
That's a great analogy. And what's really intriguing is that this descriptive redundancy, which is linked by something called gauge symmetry, is actually the key to unlocking some of the deepest mysteries in physics.
It's kind of counterintuitive, though, right? You'd think that adding more complexity would just make things more confusing. So
Right.
why is this redundancy so powerful?
That's the million-dollar question. We're going to unpack it by looking at three interconnected reasons: the methodological, geometrical,
Yep.
and the relational. Each one reveals a different facet of why this seemingly unnecessary redundancy is actually the secret weapon of modern physics.
A secret weapon. Okay, now you've really got my attention. Let's start with the methodological reason, which involves the brilliant Emmy Noether and her famous theorems.
Ah, yes. Notice theorems. They're like a Rosetta Stone for physics. They uncover these beautiful connections between symmetry and conservation
That's
laws.
physics cheat codes, right? Unveiling hidden connections between things that seem completely unrelated.
Exactly. So Noether's first theorem tells us that when you have a global symmetry in a physical system, meaning the symmetry is the same everywhere in space and time, you automatically get a conserved quantity. Think of energy conservation. It arises because the laws of physics are the same today as they were yesterday.
Right.
That's a global symmetry, and it leads to the conservation of energy.
So if the rules of the game are the same everywhere, something must always be conserved. That makes sense.
Yeah.
But what happens when the rules themselves are allowed to change from place to place? Is that where the second theorem comes in?
Precisely. Noether's second theorem deals with local symmetries, where the symmetry can vary from point to point in spacetime. Imagine that coordinate system analogy we discussed. But now the coordinates shift and morph as you move through space and time.
So it's a more flexible, dynamic kind of symmetry.
Exactly. And here's the crucial part. Noether's second theorem shows that these dynamic symmetries actually constrain the behavior of force fields.
Okay.
They ensure that forces and charges interact in a way that always respects the conservation laws.
So it's like force fields aren't random. They're shaped by symmetry to ensure the universe's books stay balanced. It's
Yeah.
like there's a built-in error-checking mechanism. Is that a fair interpretation?
That's a great way to think about it. The force fields are guided by these local symmetries, making sure everything stays consistent with the conservation laws.
Is there an analogy we could use to maybe help visualize this?
Sure. Imagine a river flowing downstream.
Okay.
The conserved charge is like the water itself, and the force field acts like the riverbanks, guiding the flow smoothly and preventing it from disappearing randomly.
Okay, I can picture that. So Noether's theorems, especially the second one, provide a powerful framework for understanding how gauge theory and conservation laws are intertwined. But how does this actually work when constructing physical theories?
Well, we can break it down into four possible scenarios.
Mm.
Imagine you have Lagrangians. These are mathematical expressions that describe the dynamics of a physical system. You can have Lagrangians either with or without a gauge potential, which represents the force field,
Yeah.
and you can have either global or local symmetries.
So we have four possibilities to explore. A Lagrangian with global symmetry, a Lagrangian with local symmetry, a Lagrangian with the gauge potential and global symmetry, and a Lagrangian with the gauge potential and local symmetry.
You got it. Now, the truly fascinating thing is what happens when you combine a gauge potential with a local symmetry.
This is where the real magic happens.
Exactly. In this scenario, the dynamics of the system automatically ensure charge conservation, even without explicitly imposing it. It's as though the theory itself inherently knows how to keep everything balanced and consistent. This is where the true power of gauge theory becomes apparent. Yeah, it's truly remarkable how gauge theory leads to such elegant and consistent physical models, but we've only just begun our exploration. Our next stop on this deep dive takes us into the realm of geometry.
So we're moving from the abstract world of Emmy Noether's theorems to something more uh, visual, more spatial.
Precisely. We're going to delve into how gauge theory can be understood through the lens of geometry, specifically the geometry of fiber bundles.
Hmm.
I know it sounds a bit intimidating, but I assure you we can make it relatable.
Fiber bundles, huh? That sounds pretty abstract. Can you, like, paint me a picture?
Okay, so think back to that temperature field we discussed earlier.
Oh.
It's like a map where every point in space is assigned a specific temperature value. Now imagine fields with more complex internal structures like vectors, where each point in space has its own little vector space attached to it.
Mm.
These structured spaces are what we call fiber bundles.
So it's like each point in space has this extra dimension of information, this little internal world of vectors associated with it.
That's a great way to put it. To understand how this connects to gauge theory, let's start with something a bit more familiar, the tangent bundle in differential geometry.
Tangent bundles. That rings a bell from calculus class, but I could use a refresher.
All right, imagine yourself walking on a curved surface like a sphere. At each point on that surface, there's a tangent plane representing all the possible directions you could walk in from that point. The collection of all these tangent planes forms what we call the tangent bundle.
Ah, okay. It's like the tangent bundle provides a guide to all the possible movements on a curved surface.
Precisely. Now, in gauge theory, we have something analogous called principal bundles. These bundles are responsible for coordinating the behavior of different matter fields that are all influenced by the same force.
So instead of a map of possible directions, it's a map of how particles are allowed to interact with each other.
You could think of it that way. It ensures that these different matter fields, even though they might have their own individual properties, all play by the same rules when it comes to interacting with a particular force.
Is there like a good analogy to illustrate this?
Sure. Picture a conductor leading an orchestra.
Okay.
Each instrument plays its own part, but the conductor ensures they all harmonize together.
I like that. So the principal bundle is like the conductor ensuring that all the different particles interacting with a force are in sync with each other.
Exactly. And this brings us to the really mind-blowing part. Those gauge transformations we talked about earlier can actually be seen as changes in the internal geometry of these bundles.
Wait, so we're not just talking about abstract mathematical transformations anymore. We're talking about actual changes in the geometry of these internal spaces.
That's precisely it. It's like in general relativity, where the curvature of space-time affects how objects move. Similarly, the curvature of these internal spaces in gauge theory dictates how particles interact with each other.
Wow. So the behavior of particles is actually governed by the geometry of these hidden internal spaces, these fiber bundles. It's like there's a whole unseen world of geometry shaping the interactions we observe in the universe.
That's a beautiful way to put it. And this perspective helps us debunk a common myth about the standard model of particle physics.
Yeah.
People often say that all the different fields in the standard model, quarks, leptons, gauge bosons, all exist in separate, unrelated spaces. But gauge theory tells us a different story.
Okay, I'm ready for another mind-blowing revelation. What's the real story?
The real story is that all these fields can be understood as existing within a single, interconnected internal space. Think of it like space-time in general relativity. But instead of describing the geometry of space and time, it describes the inner world of these fundamental particles.
So instead of imagining these particles as scattered across different spaces, we should envision them all living within one unified, interconnected landscape.
Exactly. And this viewpoint challenges the traditional interpretation of principal bundles as merely auxiliary mathematical tools. They're not just a conductor on the sidelines. They're deeply connected to the very fabric of reality itself.
That's incredible. It seems like we're starting to see a pattern here. First, we saw how symmetry guides the rules of interaction, and now we're seeing how that symmetry actually shapes the playing field itself.
You're catching on quickly. And that brings us to the most intriguing aspect of gauge theory, the relational perspective. This is where we start to explore what gauge theory might be telling us about the fundamental nature of reality itself.
Okay, I'm all ears. What's this relational perspective all about? So we've seen how symmetry shapes the rules and the playing field itself, but how does this relational perspective tie into all of this?
Well, to grasp the relational aspect, we need to look at a truly bizarre phenomenon, the Aharonov-Bohm effect.
Okay.
Imagine a region of space where there's no magnetic field, but there's a magnetic potential nearby, like a coil of wire with current flowing through it.
Right.
The Aharonov-Bohm effect demonstrates that even though particles passing through this field-free region never encounter the magnetic field itself, they're still affected by it.
So even if a particle never comes into contact with a magnetic field directly, it can still be influenced by it.
Yeah.
That's incredibly counterintuitive. It almost suggests that there's more to reality than what we can directly observe.
It's one of those things that makes you question your assumptions about how the universe works. And it gets even stranger in non-abelian gauge theories, like those describing the strong and weak forces. Even in areas where the field strength is zero and the topology is simple, the gauge potentials still hold information that goes beyond the curvature.
It's like the particles are somehow sensing the potential for a magnetic field, even if the field itself isn't present. It's as though they're aware of the possibilities, not just the actualities.
That's a very insightful observation.
Yeah.
And this is where the work of physicist Carlo Rovelli comes into play. He argues that the Aharonov-Bohm effect and other phenomena related to gauge potentials hint at a profound truth. The universe is fundamentally relational.
Okay, I'm intrigued. Tell me more about Ravelli's argument.
Think about it this way. When you want to describe the location of two objects, it's not their absolute positions that are most important.
Right.
It's the distance between them,
Yeah.
right?
Yeah.
That distance is a relational quantity. Ravelli proposes that gauge symmetries are all about these kinds of relational quantities.
So instead of focusing on individual particles and their properties, we should be looking at the relationships between them, how they're connected, how they interact, how they're entangled. It's like the connections themselves are more fundamental than the things being connected.
Precisely.
Mm.
Just as the distance between 2 points is more fundamental than their absolute coordinates, the relationships between particles, like their relative orientations in those internal spaces we discussed, are crucial to understanding gauge theories. It's the relationship that defines the reality, not the individual entities in isolation.
So gauge theory is not just a convenient mathematical tool. It's pointing to a profound truth about the interconnected nature of reality. It's like we're shifting our perspective from a universe of isolated objects to a universe of intertwined relationships.
That's a great way to summarize it. And this shift in perspective has significant implications for some of the biggest questions in physics, such as the nature of locality and separability. Can we truly divide the universe into neat, independent parts, or is it all fundamentally entangled, interconnected at the deepest level?
Those are some big questions. Is there an example you can give that illustrates this idea of non-separability?
Consider entangled particles. When you measure the state of one particle, the state of the other particle is instantly affected, even if they're light years apart.
Oh.
That's a form of non-separability.
Yeah.
And it's closely linked to these gauge symmetries we've been discussing.
So it's like the universe is playing a cosmic game of connect the dots.
Uh-huh.
And gauge theory is revealing the hidden threads that link everything together. This has been an incredible journey. We started with this seemingly counterintuitive idea of using a redundant language to describe physics. And we've uncovered 3 compelling reasons why this redundancy is so powerful: the methodological, the geometrical, and the relational.
And as we've seen, these 3 reasons are deeply intertwined. Gauge symmetry acts as a guiding principle shaping the rules of interaction and the very fabric of the spaces where those interactions occur. But perhaps most importantly, gauge theory suggests that the universe is fundamentally interconnected, woven together by a tapestry of relationships.
We've covered a lot of ground in this deep dive, from abstract mathematical theorems to a mind-boggling geometrical picture to a profound relational view of the universe. It's clear that gauge theory is much more than just a set of equations. It's a framework for understanding the most fundamental connections in the cosmos.
I couldn't agree more. And as with any good exploration, our deep dive has unearthed more questions than answers. But it's these questions that drive us to keep searching, to keep pushing the boundaries of our understanding.
Speaking of questions, what's one final thought-provoking question you'd like to leave our listener with? Something to ponder as they continue their exploration of gauge theory.
If the universe is truly relational, woven together by this web of gauge symmetries, what does that tell us about the fundamental building blocks of reality? Are they particles, fields, or something else entirely, something even more interconnected and holistic than we can currently imagine? That's something I encourage everyone to contemplate as they delve deeper into this fascinating and profound subject.